Hey guys, tonight we're diving into one of the most powerful and world changing scientific developments in human history, the atomic bombings. We'll explore the science behind how it all worked, from the invisible forces that hold the atom together to the incredible breakthroughs that unlocked its energy, to the engineering marvels that turned theory into devastating reality. So before you get too comfortable, take a moment to like and subscribe, but only if you enjoy the kind of content that merges myth and mystery. And hey, let us know from where you're watching from and what time it is for you right now. It's time now to dim the lights, settle in, and let's cover what we have for tonight together. If you were to look around your room right now, you'd see walls, light, air, ordinary things that seem solid and still. But within every bit of that quiet matter lies a world so small, so intricate, and so powerful that unlocking it once changed the course of human history. This world is built from atoms, the tiny, invisible building blocks of everything you see, touch, and breathe. Tonight, we begin by understanding what an atom truly is, and how something so unimaginably small could one day reshape entire cities in a blinding instant. The idea of the atom isn't new. In fact, the word itself comes from ancient Greece, atomos, meaning indivisible. Philosophers like Democritus imagined that if you kept dividing a piece of matter, a rock, a leaf, a drop of water, eventually you'd reach something so small it could no longer be divided. That was the atom. For centuries, this was a purely philosophical idea, with no proof, no instruments to see it, and no reason to believe it was more than poetic speculation. But the 19th and early 20th centuries transformed philosophy into physics through the work of scientists like John Dalton, J.J. Thomson, Ernest Rutherford, and Niels Bohr. The atom was not only proven to exist, it was dissected, diagrammed, and measured. What they found was nothing short of revolutionary. Imagine a model of the atom, not as a miniature marble, but as an almost empty sphere. At the center lies a tiny, dense core, the nucleus, containing nearly all of the atom's mass. Within that nucleus are two kinds of particles: protons, which carry a positive electric charge, and neutrons, which carry no charge at all. Around this nucleus, like planets around a star, orbit electrons, minuscule particles with a negative charge, moving at incredible speeds. If the nucleus were the size of a marble, the nearest electron would be several meters away. In other words, atoms, and therefore everything we know, are mostly empty space. But that little marble at the center, the nucleus, hides something astonishing. It's held together by what physicists call the strong nuclear force, the most powerful known force in the universe. It's far stronger than gravity, far stronger than the electrical attraction between electrons and protons. This force binds protons and neutrons together so tightly that separating them releases unimaginable energy. To understand how powerful that force is, let's recall the relationship Einstein revealed in 1905. E mc2, energy equals mass multiplied by the speed of light squared. The speed of light, about 300 million meters per second, is such an enormous number that even a tiny bit of mass can yield an enormous amount of energy. For example, converting just 1 gram of matter, less than a paperclip, completely into energy would release the same amount of energy as about 21,000 tons of TNT. That is the principle underlying both nuclear power and nuclear weapons. But here's the catch. Under ordinary conditions, the nucleus doesn't just fall apart. It's astonishingly stable. The strong force is so effective that it resists the repulsive electrical forces between the positively charged protons. So, for centuries, despite all the atoms surrounding us, that vast reservoir of nuclear energy remained sealed, hidden from view, locked inside nature's tiniest vault. At the dawn of the 20th century, scientists began to notice subtle clues that the atom wasn't entirely unbreakable. The discovery of radioactivity by Henri Becquerel and the work of Marie and Pierre Curie showed that certain atoms could spontaneously emit particles and transform into different elements. The nucleus could change, meaning it wasn't indestructible after all. Each decay released small bursts of energy, often as invisible rays or tiny particles traveling at incredible speeds. But those early experiments revealed only a faint whisper of what the nucleus truly contained. When Ernest Rutherford conducted his famous gold foil experiment in 1909, firing alpha particles at thin sheets of gold, he made a discovery that redefined atomic structure. Most of the particles passed straight through, proof that atoms were mostly empty, but some bounced back, as if they had struck something dense and impenetrable. Rutherford had found the nucleus, a speck of immense density at the atom's heart. As scientists learned more, they discovered that atoms could not only decay naturally, but could also be transformed by human intervention. By bombarding atoms with high-speed particles, they could make the nuclei break apart or fuse together. For the first time in history, human beings could alter the building blocks of matter itself. Still, the true power of the atom remained a mystery. The energies released in these experiments were tiny, measurable, yes, but not yet practical. It was only when physicists began working with the heaviest elements, like uranium, that they started to see something extraordinary. Uranium nuclei are large and unstable, teetering on the edge of balance. It wouldn't take much, just a small nudge, to split one apart completely. When that happens, the nucleus divides into two smaller nuclei and releases not only a tremendous amount of energy, but also several free neutrons. These neutrons, in turn, can strike other uranium atoms, causing them to split as well, each releasing more energy and more neutrons. If this chain of events continues fast enough, the number of fissions multiplies exponentially. This is the secret mechanism of the atomic bomb. But before we get ahead of ourselves, it's important to grasp what makes that process possible at all. When a uranium nucleus splits, a fraction of its mass, only about 1/10 of 1%, disappears. That missing mass has been converted into pure energy, according to Einstein's formula. It's not chemical energy, like burning fuel or wood. It's not heat from friction or compression. It's something entirely different. Energy drawn directly from the mass of matter itself. In this sense, the atomic bomb wasn't just a weapon, it was a demonstration of nature's deepest principle. It showed that the universe stores vast quantities of energy in every grain of existence. Every stone, every drop of water, every cell in our body contains within it the same potential, the same balance between mass and energy that fuels stars and galaxies. Of course, unlocking that power required immense human ingenuity. The scientists of the early 20th century didn't set out to build bombs. They were explorers of the invisible, driven by curiosity to understand how matter works. The discovery of the atom's structure, the understanding of radioactivity, and the revelation of the strong nuclear force were all steps toward one of the most transformative realizations in science, that the universe is both delicate and explosive, calm on the surface, yet filled with infinite energy below. By the time humanity grasped that truth, the world was already at war. Nations raced to apply these discoveries, and laboratories that once studied cosmic rays and crystal structures became the centers of a new kind of research, one that could release the power of the atom on command. But tonight, before we move into the machines, the laboratories, and the explosions, it's worth pausing here, at the core of everything, to appreciate the strange, elegant, and terrifying simplicity of the atom. It is a universe in miniature, governed by forces invisible, yet absolute, and hidden inside it, waiting quietly, is the same power that burns in the heart of stars. When we talk about the atom, we often imagine it as a simple structure, a compact nucleus surrounded by electrons, quietly existing in perfect balance. But deep inside that nucleus lies a struggle, an invisible contest of forces, attraction versus repulsion, creation versus destruction. This silent conflict defines not just the stability of the atom, but the foundation of nuclear energy itself. To truly understand how humanity split the atom, we must first understand what holds it together. This is the story of nuclear binding energy, the glue of the universe. Let's begin with the heart of the atom, the nucleus. It's made up of protons and neutrons, collectively known as nucleons. Each proton carries a positive electric charge, while each neutron has no charge at all. The fact that multiple protons can exist side by side in a tiny space without immediately flying apart is one of the most astonishing feats of nature. After all, like charges repel, and the repulsive electrical force between two protons is enormous. Yet somehow, in every stable nucleus, this repulsion is overcome by another, even stronger force, the strong nuclear force. The strong force acts between all nucleons, protons, and neutrons alike. It's an attractive force, but it operates only at extremely short distances, less than a femtometer or 1/trillionth of a millimeter. Within this minuscule range, it's powerful enough to dominate over the repulsive electric forces. But step just a little farther out, and it fades almost instantly to nothing. It's as though the nucleus exists in a state of delicate tension, a balance between the incredible pull of the strong force and the constant outward push of electrostatic repulsion. So, how strong is the strong force? To get a sense of scale, imagine this. If the electrical repulsion between protons were like the force between two powerful magnets, the strong force would be like an industrial clamp that could crush steel beams together, but only if those beams were within a hair's width of touching. It's fierce, but fleeting. Now, every time a nucleus forms, when protons and neutrons bind together, something remarkable happens. The total mass of the bound nucleus is actually less than the combined mass of its individual particles. It's as if some of the mass simply vanishes. This missing mass hasn't disappeared, though. It's been converted into energy, the binding energy that holds the nucleus together. According to Einstein's E, MC2, even the smallest loss of mass represents a tremendous amount of energy. The greater the binding energy, the more stable the nucleus. Let's take a familiar example. Helium. A helium nucleus contains 2 protons and 2 neutrons. If you add up their individual masses, you get a slightly larger number than the actual mass of the helium nucleus. The difference corresponds to about 28 million electron volts, MeV of energy. That is the energy that would need to be supplied to tear the nucleus apart into separate protons and neutrons again. In other words, binding energy is the measure of how tightly nature holds its matter together. Across the periodic table, each element has its own characteristic binding energy per nucleon. Light elements like hydrogen and helium have relatively low binding energies. Mid-range elements like iron and nickel have the highest. In fact, iron 56, a stable isotope of iron, sits at the very peak of the binding energy curve. That means it's the most stable configuration of nuclear matter known. It's no coincidence that the cores of stars, after millions of years of fusion, end up filled with iron. The universe itself tends toward stability. The shape of this binding energy curve explains 2 very different but equally powerful nuclear processes: fusion and fission. Fusion happens when light nuclei combine to form a heavier one. In doing so, they move up the curve toward higher binding energy, releasing the difference as energy. This is what powers the sun. Every second, in the core of the sun, around 600 million tons of hydrogen are fused into helium, releasing energy that sustains life on Earth. The energy comes from the small mass difference between the raw hydrogen nuclei and the helium nucleus they form. Just a fraction of a percent, but multiplied by C2, it's enough to light up a star. Fission, on the other hand, occurs at the opposite end of the curve, when a very heavy nucleus, like uranium 235 or plutonium 230 splits into 2 smaller nuclei. The resulting fragments are closer to the middle of the curve. Again, closer to iron. The total binding energy per nucleon increases, meaning the system has released energy. It's as if the nucleus relaxes into a more stable configuration, giving off the excess energy as heat, light, and radiation. The energy per fission event might seem small, around 200 MeV, but remember, that's for a single atom. A gram of uranium contains about 2.6 grittos-21 atoms. When you multiply that number by the energy per atom, you get something staggering, roughly 80 trillion joules of energy, the same as detonating 20,000 tons of TNT. And that's from a single gram. What's truly fascinating is that this energy isn't exotic or magical. It's not created from nothing. It's a natural consequence of how the fundamental forces of nature organize matter. The universe simply rewards stability. When matter rearranges itself into a more tightly bound state, it releases the difference as energy, just as a falling rock releases potential energy when it drops to the ground. But here's the subtlety that makes nuclear science both challenging and extraordinary. Achieving those rearrangements is not easy. Nuclei are extremely resistant to change. For example, to make 2 protons fuse, you must overcome their powerful electrical repulsion, the so-called Coulomb barrier. In stars, that's achieved through immense temperature and pressure. To make uranium fission, you need to deliver just the right energy to make its nucleus wobble and split. typically by hitting it with a neutron. When a neutron strikes a uranium-235 nucleus, it's absorbed, making the nucleus temporarily heavier and more unstable. The new configuration deforms like a drop of liquid stretched too far. In a moment of instability, the nucleus divides into two smaller nuclei, and several neutrons fly free, carrying kinetic energy. Those neutrons can then collide with other uranium atoms, continuing the process, a chain reaction. That's where the concept of critical mass comes into play. You need enough material for the released neutrons to keep finding new targets, sustaining the reaction. All of this, the balance between forces, the conversion of mass to energy, the chain reaction, ultimately comes back to the same simple truth: the binding energy curve. It's the master key to the atom's behavior. It determines which elements can fuse, which can fission, which are stable, and which will decay. It defines the lifespan of stars and the lifespan of radioactive isotopes alike. The more you study this curve, the more you see a kind of poetry in it. Nature seems to prefer balance. Light atoms join together to reach stability. Heavy atoms split apart for the same reason. The total energy of the universe remains constant. It's merely rearranged, transformed from one form to another, always seeking equilibrium. When the scientists of the 1930s realized this, when they understood that splitting uranium could unleash the same kind of energy that powers stars, they knew they had uncovered a fundamental secret of existence. It wasn't just about making a weapon. It was about seeing the hidden architecture of the cosmos. Every nucleus, no matter how small, was a miniature reflection of universal forces: gravity, electromagnetism, and that mighty strong force that glues it all together. And in the years that followed, that understanding would be turned from theoretical curiosity into a tool of extraordinary power. To use it, humanity would need to build the first machines capable of manipulating atoms one by one: reactors, cyclotrons, and accelerators. The next step in our journey takes us to the moment when this understanding of nuclear binding energy would evolve into something even more profound: the discovery of fission itself. By the late 1930s, the world of physics stood on the edge of a revelation. The atom, once thought indivisible, had already been cracked open. Scientists had learned how to strip electrons away, to bombard nuclei with subatomic projectiles, and to transmute one element into another. But no one yet understood the full potential of these experiments. The nucleus, so small it could never be seen, was about to reveal a secret that would shake both science and civilization. It began, as many discoveries do, with curiosity and a few puzzling results. In Berlin, two German chemists, Otto Hahn and Fritz Strassmann, were conducting experiments in nuclear chemistry. Their goal was to study what happened when uranium, the heaviest naturally occurring element, was bombarded with neutrons. The neutron, discovered only a few years earlier by James Chadwick in 1932, was an ideal projectile. It carried no electric charge, so it could slip past the electrical defenses of the nucleus without being repelled. At the same time, in other parts of Europe, physicists like Enrico Fermi in Italy had already fired neutrons into elements across the periodic table. Fermi believed he had created new elements beyond uranium, what he called transuranic elements. He was wrong, but the confusion was understandable. The nuclear reactions were complex, and the analytical tools of the day couldn't easily identify the products. The atomic nucleus was still a mystery box, and scientists were just beginning to learn how to open it. So Hahn and Strassmann continued Fermi's work with refined precision. They bombarded uranium with slow neutrons, then carefully analyzed the radioactive products that formed. Their method was meticulous, a combination of chemistry and physics, where the invisible was made tangible through chemical separations and radioactive decay measurements. But what they found was baffling. Among the products of their experiments, they detected barium, a much lighter element with only about half the atomic mass of uranium. According to everything known at the time, this should have been impossible. Bombarding a heavy nucleus like uranium was supposed to nudge it slightly, maybe make it emit a small particle, or create a slightly heavier element. It wasn't supposed to cut the atom in half. At first, Hahn himself didn't believe it. Barium was far down the periodic table, a product one would expect if the uranium nucleus had split into two large fragments. But that was unthinkable. The atom was known to be stable, almost invincible. What could possibly cause it to break apart so completely? Unsure of how to interpret his results, Hahn wrote a letter to his longtime collaborator and friend, Lise Meitner, an Austrian-born physicist who had fled Nazi Germany to Sweden months earlier because of her Jewish heritage. Meitner had been one of the most brilliant nuclear physicists of her time. Reading Hahn's data, she immediately sensed that something extraordinary had occurred. Over the Christmas holidays of 1938, Lise Meitner and her nephew, physicist Otto Frisch, took a long walk in the snowy woods of Sweden. They discussed the puzzle of the uranium results, turning over every possibility in their minds. Could the uranium nucleus really have split? If so, what force could explain it? As they walked, Meitner recalled the liquid drop model of the nucleus, a theory proposed by Niels Bohr. In this model, the nucleus behaves like a drop of liquid, cohesive but deformable. When it absorbs energy, it can wobble, stretch, and, if overstressed, split into two smaller drops. Meitner realized that when a uranium nucleus absorbs a neutron, it becomes momentarily unstable, heavier, deformed, and vibrating violently under the immense strain of electrical repulsion between its protons. It could stretch and tear apart. She did some quick calculations on a scrap of paper. The energy released from the mass difference between uranium and the two smaller nuclei, according to Einstein's E proud MC2, was about 200 million electron volts, MeV. That was an extraordinary number. Typical chemical reactions release only a few electron volts per atom. This was 100 million times more powerful. Right there, in that quiet winter landscape, Meitner and Frisch realized they were looking at a completely new phenomenon, the fission of the uranium nucleus. They coined the term fission by analogy with biological cell division, and just as a single cell dividing can create new life, a single nucleus splitting could release a burst of pure energy, unseen and unimagined until that moment. In early 1939, their interpretation was published, confirming what Hahn and Strassmann had accidentally discovered in the lab. The scientific world erupted with excitement. Across Europe and America, physicists raced to replicate the experiment, and within weeks, laboratories in Paris, Copenhagen, and Berkeley confirmed the findings. The impossible had become real. The nucleus of uranium could indeed split into two roughly equal parts, releasing enormous energy and additional neutrons. Those emitted neutrons were the key. If one neutron could cause a fission that released more neutrons, then those neutrons could, in turn, cause further fissions. The process could multiply, a chain reaction. Theoretically, such a reaction could sustain itself, each fission feeding the next. It would release energy not in a slow, controlled way, like burning coal, but explosively, in microseconds. The implications were immediate and profound. Scientists began calculating the critical mass, the minimum amount of uranium needed to sustain a chain reaction. They studied how neutrons might be slowed down, absorbed, or reflected. Physicists like Niels Bohr and Enrico Fermi speculated that a particular isotope of uranium, uranium-235, might be responsible for fission, while the more common, uranium-238, was not. Others explored whether a new artificial element, plutonium, could also undergo the same process. It was a moment of thrilling discovery and dawning dread. The world was sliding toward war. Germany, where fission had first been discovered, was now under the control of Adolf Hitler. Many of Europe's top scientists, including Meitner and Einstein, had fled to safer countries, carrying with them the knowledge that a new kind of energy was possible and that it could be weaponized. In 1939, physicist Leo Szilard, who had long feared that nuclear chain reactions could be used for destructive purposes, drafted a letter to U.S. President Franklin D. Roosevelt. Einstein signed it. The letter warned that Germany might be developing a weapon based on uranium fission. It was a cautious but urgent message, and it set in motion what would become the Manhattan Project, the vast secret effort to harness fission for war. But long before the first reactors or bombs were built, fission itself remained a scientific marvel, a phenomenon so powerful that it seemed almost alien. For the first time, humans had reached into the heart of matter and found that it could be torn apart, releasing the energy of the stars. It's important to realize how revolutionary this was. Until that moment, energy had always come from the outer layers of matter, chemical reactions involving electrons, bonds between atoms. Fission came from the core itself. It opened a new domain of energy, a deeper layer of nature's structure, one that operated on timescales and magnitudes beyond anything humanity had ever touched. The discovery of fission was not just a step forward in physics, it was a step into a new age, one where the barriers between knowledge and destruction grew perilously thin. Yet it all began not in a military lab, but in a quiet chemistry experiment with a few grains of uranium, a stream of neutrons, and two scientists asking questions that no one else thought to ask. If the discovery of fission revealed that the atom could be split, the realization of the chain reaction revealed that it could be multiplied, that one act of division could lead to countless others. It was the turning point when the power of the atom ceased to be merely theoretical and became something that could, under the right conditions, grow without limit. The chain reaction is, quite simply, the mechanism that makes both nuclear reactors and nuclear bombs possible. To understand it, imagine striking a match. One spark ignites the tip, which ignites the next bit of wood, which produces heat that lights more of the match. It's a process of propagation, one event triggering the next. Now, imagine that instead of fire, you're dealing with neutrons, and instead of wood, you're dealing with atomic nuclei that can split apart. The principle is the same, but the scale is incomparably greater. In every fission event, a uranium-235 nucleus absorbs a neutron, becomes unstable, and splits into two smaller nuclei, what we call fission fragments, while releasing an immense burst of energy and, crucially, between 2 and 3 new neutrons. Those neutrons are the seeds of a potential chain reaction. If at least one of them goes on to cause another fission, the process can continue indefinitely. But sustaining such a chain reaction requires delicate balance. If too few neutrons hit new uranium nuclei, the reaction dies out. If too many do, the process grows uncontrollably, leading to an explosion. The secret lies in managing the conditions that allow a reaction to be critical, that is, self-sustaining but stable. When physicists talk about a chain reaction, they often describe it in terms of multiplication factor, symbolized as K. If K is less than 1, the reaction fizzles out because not enough neutrons continue the process. If K equals 1, the reaction is steady. Each fission leads to exactly one more. And if K is greater than 1, the reaction accelerates exponentially. In a reactor, scientists aim to keep K precisely at 1. In a bomb, it's designed to be far greater than 1 for a fraction of a second, enough to release catastrophic energy before the device disassembles itself. Now, what makes this so complicated is that neutrons are tricky to control. After being released in fission, they move at astonishing speeds, roughly 20,000 kilometers per second, or about 7% of the speed of light. Such high-speed neutrons, known as fast neutrons, have a smaller chance of causing further fissions in uranium-235 because they zip past nuclei too quickly to be absorbed efficiently. Ironically, slowing them down makes them far more effective. That's why scientists talk about moderation, the process of slowing neutrons to thermal speeds using a moderator like water, graphite, or heavy water. At thermal speeds, neutrons have just the right amount of kinetic energy to be captured by uranium-235 nuclei, dramatically increasing the probability of fission. This is a fundamental difference between a nuclear reactor and a bomb. A reactor uses moderation and control rods to keep the chain reaction steady and continuous. A bomb, by contrast, avoids moderation altogether. It depends on a supercritical mass of material so dense that the chain reaction runs to completion almost instantaneously. The first person to truly understand the implications of a chain reaction was Leo Szilard, a Hungarian physicist and one of the unsung architects of nuclear science. In 1933, long before fission was discovered, Szilard was walking in London when he suddenly imagined the concept of a self-sustaining nuclear chain reaction. He realized that if one reaction could release particles that triggered others, the process could produce an ever-growing release of energy. He even patented the idea of a neutron-induced chain reaction, though at the time it was purely theoretical. No one yet knew of an element capable of supporting it. When fission was discovered in uranium in 1938, Szilard immediately recognized that this was the missing piece. Within a few weeks, he and physicist Enrico Fermi began working on experiments to see if such a reaction could be achieved in practice. In early 1939, at Columbia University in New York, they arranged uranium oxide and neutron sources in various configurations, searching for any sign of neutron multiplication. The experiments were crude by today's standards. Piles of uranium and paraffin, Geiger counters clicking faintly, but the goal was historic, to see if nature's smallest parts could amplify themselves into something self-sustaining. What they were doing was, in essence, measuring K. Every neutron released could either escape, be absorbed without causing fission, or trigger another fission. The geometry, density, and composition of the uranium determined the outcome. Szilard realized that the configuration itself was critical. If the uranium were spread too thin, neutrons would simply escape before colliding with new atoms. But if it were concentrated enough, if it formed a sufficiently large and dense mass, then many of those neutrons would stay inside long enough to cause further fissions. This concept became known as critical mass. The idea of critical mass is deceptively simple, but absolutely fundamental. It represents the threshold where the probability of sustaining a chain reaction crosses from impossible to inevitable. The exact amount depends on several factors: the type of fissile material, its purity, its shape, and whether there are materials around it to reflect escaping neutrons back inside. For uranium-235, the critical mass in a bare sphere is roughly 52 kilograms, but with a good neutron reflector, like a layer of uranium-238 or beryllium, it can be reduced dramatically. By 1942, scientists had begun to refine these ideas into precise engineering. The same physics that could lead to an explosion could also be tamed for steady energy production. Enrico Fermi, leading a small team at the University of Chicago, constructed the first controlled chain reaction in history, the Chicago Pile 1. It wasn't a weapon, it was a crude experimental reactor built beneath the stands of a football field. The structure consisted of layers of graphite blocks serving as a moderator, interspersed with lumps of uranium metal and uranium oxide. On December 2, 1942, Fermi and his team slowly withdrew the control rods, long cadmium rods that absorbed neutrons, until the pile reached a self-sustaining state. A simple counter clicked steadily, marking the rhythm of the world's first man-made nuclear reaction. In that quiet, dimly lit space, surrounded by graphite bricks and uncertainty, humanity had achieved the impossible: self-sustaining release of energy from the atomic nucleus. The principles that governed that small pile would later be scaled up into reactors and miniaturized, accelerated, and weaponized into bombs. What made all of this possible was not brute force, but mathematics and geometry. The behavior of neutrons followed precise statistical laws. Physicists could calculate the mean free path, the average distance a neutron traveled before striking another nucleus, and use that to determine the optimal size and density of the fissile mass. They could predict the neutron multiplication factor from cross-section data and geometry. The bomb was born not from chaos, but from equations that described how probability could be shaped into certainty. The beauty and danger of the chain reaction lies in its feedback. Once started, it builds upon itself faster and faster. In a reactor, delayed neutrons, emitted fractions of a second after fission, provide a natural break, giving operators time to control the process. In a bomb, where the goal is total release. These delayed neutrons are irrelevant. The reaction proceeds on the order of microseconds, far faster than any human or mechanical intervention. The result is an exponential avalanche of energy, billions of reactions occurring almost simultaneously. It's worth imagining what that means. In a critical mass of uranium, just one neutron sets off a cascade. In the first generation, one atom splits. In the second, two. Then 4, 8, 16. The numbers doubling each time. After only 80 generations, less than a microsecond, almost all the fissile material has undergone fission. The number of reactions exceeds 10 to the 24th power. The amount of energy released is equivalent to tens of thousands of tons of TNT, all in an instant. The chain reaction, at its heart, is a demonstration of nature's own amplification system. It shows how, from the quiet split of a single atom, the universe can multiply energy beyond comprehension. It was the mechanism that took the hidden power of the nucleus and turned it into something both astonishing and terrifying, a process that would soon light the desert skies of New Mexico and alter the destiny of nations. By 1939, the world was teetering on the brink of conflict. Scientists had unlocked a secret that could unleash unimaginable energy. The nucleus could be split, producing both enormous heat and an avalanche of neutrons capable of sustaining a chain reaction. Fission was no longer a theoretical curiosity. It had the potential to be weaponized, and as Europe descended into war, the question became urgent. Who would harness this power first? The answer began with a letter. In August 1939, physicists Albert Einstein and Leo Szilard, both deeply aware of the implications of fission, wrote to U.S. President Franklin D. Roosevelt. The letter warned that Germany might already be attempting to develop a weapon based on uranium fission and suggested that the United States should accelerate research into atomic energy. Einstein's signature gave the letter authority. Szilard's technical insight provided substance. This seemingly simple correspondence sparked one of the largest and most secretive scientific undertakings in history, the Manhattan Project. The Manhattan Project was not a single laboratory or a single city. It was a sprawling network of research facilities, industrial plants, and testing sites scattered across the United States. Its name was deliberately misleading, suggesting some kind of harmless office work in Manhattan, while in reality, it became the crucible in which the most powerful weapon in human history would be forged. At its head was General Leslie Groves, a career Army officer tasked with managing construction, security, logistics, and overall coordination. On the scientific side was J. Robert Oppenheimer, a theoretical physicist known for his brilliance and intense focus. Groves and Oppenheimer represented two halves of a single mission: military precision and scientific ingenuity, a combination that would define the project's extraordinary success. The Manhattan Project's scale was staggering. At its height, it employed over 130,000 people: physicists, chemists, engineers, metallurgists, and laborers. Laboratories were constructed from the ground up, including Los Alamos, New Mexico, designed specifically to house theoretical and experimental physicists. Oak Ridge, Tennessee, became the center for uranium enrichment, while Hanford, Washington, focused on producing plutonium. Each site was a marvel of engineering and secrecy. with its own specialized purpose, yet all were interconnected toward the singular goal of creating an atomic weapon. The urgency of the project was palpable. Scientists understood that if Nazi Germany succeeded first, the consequences could be catastrophic. Yet the task was daunting. Producing enough fissile material, either uranium 235 or plutonium 239, required industrial processes that had never been attempted on such a scale. Enrichment facilities had to be massive, complex, and precise. Plutonium production demanded nuclear reactors and chemical separation plants, dealing with materials that were highly radioactive and volatile. The Manhattan Project wasn't just a scientific experiment, it was an engineering and logistical feat of unprecedented magnitude. Oppenheimer's role at Los Alamos was unique. He gathered some of the brightest minds of the era, including Niels Bohr, Hans Bethe, Richard Feynman, and Edward Teller, into a single research hub. The goal was to design a bomb that could produce a controlled, explosive chain reaction. The team had to answer questions that had never been solved. How do you assemble a supercritical mass? How do you ensure the reaction happens uniformly and instantaneously? How do you handle material that is highly unstable and radioactive? Each of these questions required theoretical calculations, experimental verification, and imaginative engineering solutions. The Manhattan Project also blurred the line between pure science and applied technology. Theoretical physicists worked alongside chemists and metallurgists. They studied neutron cross-sections, critical mass calculations, and the behavior of fast neutrons. Meanwhile, engineers developed the infrastructure to handle tons of uranium and plutonium safely. Every advance in theory had to be matched by an industrial process capable of producing and controlling fissile material at scale. Secrecy was paramount. The project operated in strict compartmentalization. Most workers did not know what they were producing or why. Many at Oak Ridge, for example, thought they were working on conventional chemical processes. Security measures were intense, with military police patrolling plants and scientists forbidden from discussing their work outside of secure facilities. Letters were censored, photographs prohibited, and phone calls monitored. The Manhattan Project existed in a bubble of classified knowledge, yet its consequences would soon extend across the entire world. One of the most significant challenges was selecting which type of bomb to pursue. Scientists quickly realized there were two paths: a uranium 235 gun-type bomb and a plutonium 239 implosion bomb. The uranium bomb was conceptually simpler. Two subcritical pieces of uranium would be fired together to form a supercritical mass. The plutonium bomb required far more complex engineering, using explosives to compress the plutonium into a supercritical state in a precise, symmetrical manner. Both designs demanded intensive experimentation, calculations, and testing. The Manhattan Project wasn't just a scientific effort, it was a demonstration of interdisciplinary collaboration on a scale never before seen. Chemists, engineers, and metallurgists solved practical problems that theorists alone could not. They developed techniques to purify uranium and plutonium to unprecedented levels. They designed detectors capable of measuring neutron flux with extraordinary precision. They calculated the exact timing needed for detonators in an implosion bomb, synchronization accurate to microseconds. Every aspect of the project required a combination of imagination, mathematical rigor, and meticulous engineering. By 1945, the project had achieved remarkable results. Enough fissile material had been produced to consider building operational weapons. The theoretical models had been validated in laboratory experiments. All that remained was to assemble the bombs and test the implosion design, a challenge met with the first detonation at the Trinity test in July 1945. That desert explosion would be the culmination of 6 years of concentrated effort, thousands of brilliant minds, and industrial processes operating at the limit of human capability. The Manhattan Project is often remembered as a race against time, a fusion of science, military strategy, and industrial might. It was, in every sense, a turning point in human history. It demonstrated that when humanity understands the fundamental forces of nature, we can channel them for creation, for destruction, and for knowledge itself. The discovery of fission, the understanding of chain reactions, and the realization of critical mass all converged in this massive, secret effort. It is important to recognize that while the Manhattan Project is often associated with bombs, it was also a profound achievement in physics and engineering. It required the creation of technologies and methodologies that would later influence nuclear power, medical isotopes, and the study of fundamental particles. The knowledge generated, neutron cross sections, reactor physics, isotope separation, laid the foundation for peaceful nuclear science as much as for weapons. By the time the project moved toward testing and deployment, it had transformed the world's understanding of what was possible. It had proven that the atom, once thought indivisible, could be not only split, but controlled. And that control, the result of precise calculations, experiments, and engineering, would soon demonstrate, in an almost unimaginable way, the raw power that lies hidden within matter itself. The Manhattan Project, in essence, was where theory became reality. It was where curiosity and mathematics met industrial scale experimentation. It was the bridge between understanding nuclear forces in a laboratory and harnessing them on a scale large enough to alter the course of human civilization. And it all began with a single insight: that the nucleus could be split, that a chain reaction could be self-sustaining, and that humanity was now capable of releasing energy from the heart of the atom. By the time the Manhattan Project was fully underway, it had become more than a research initiative. It was a vast, sprawling scientific empire. The scale of the undertaking was staggering, a combination of unprecedented human collaboration, industrial power, and advanced scientific theory, all focused on one extraordinary goal: to harness the energy hidden in the nucleus of the atom. To truly appreciate what was achieved, it helps to examine the empire that scientists and engineers built, the remarkable facilities they created, and the brilliant minds who brought theory to reality. At the center of this empire was Los Alamos, New Mexico, a remote plateau in the high desert chosen for its isolation and security. It became the headquarters for bomb design and theoretical physics. Unlike conventional laboratories, Los Alamos was a city-sized facility, a self-contained scientific metropolis. Barracks, offices, mess halls, and laboratories were constructed from scratch, all under tight military oversight. The desert offered a unique advantage. The wide open space allowed for experimentation, testing, and research without prying eyes. Here, the most brilliant physicists of the era would spend years in intense focus calculating critical masses, neutron fluxes, and implosion geometries. J. Robert Oppenheimer, often referred to as the father of the atomic bomb, led Los Alamos with a combination of intellectual brilliance and magnetic personality. He drew together some of the greatest scientific minds of the 20th century, creating a collaborative environment where pure theoretical physics met practical engineering. The roster of talent included luminaries such as Niels Bohr, who brought deep insights into nuclear structure and quantum mechanics, Hans Bethe, who tackled the complex calculations of energy release, and Richard Feynman, known for his unorthodox problem-solving approaches and ability to translate abstract theory into practical solutions. This assembly of minds was unparalleled in history, a concentrated force of human intellect dedicated to one task. While Los Alamos focused on theory and design, other components of the scientific empire handled the monumental task of producing fissile material. At Oak Ridge, Tennessee, engineers tackled the enormous challenge of separating uranium-235 from uranium-238. Natural uranium contains less than 1% of the fissile isotope uranium-235, so enrichment was critical. Oak Ridge became a site of industrial ingenuity. Massive plants housed gaseous diffusion and electromagnetic separation systems, each consuming vast amounts of electricity and requiring precise mechanical tolerances. The scale was unprecedented. Thousands of workers operated machines that extended over acres, all moving minuscule quantities of uranium with extraordinary precision. Simultaneously, at Hanford, Washington, the focus was on plutonium production. Plutonium-239 doesn't occur naturally in significant quantities. It had to be synthesized by bombarding uranium-238 with neutrons in nuclear reactors. These reactors were massive structures containing tons of uranium and heavy water moderators to slow neutrons. After irradiation, highly radioactive plutonium had to be chemically separated from the uranium and fission products, a process so dangerous that the design of the chemical plants required both innovation and careful attention to radiation shielding. At Hanford, teams of chemists, engineers, and laborers performed feats that combined industrial engineering with cutting-edge nuclear chemistry, all while avoiding deadly contamination. The empire also extended into logistics, construction, and administration, transporting fissile materials, managing security, and coordinating research across thousands of personnel required a military-style organization. General Leslie Groves, the military director of the project, oversaw the construction of sites, acquisition of resources, and the secrecy necessary to prevent the Axis powers from discovering the program. Supplies, from specialized metals to cutting-edge detectors, had to be sourced and delivered on a massive scale. The project consumed enormous amounts of steel, copper, and electricity, an industrial effort rivaling wartime production for tanks and planes. One of the remarkable aspects of building this empire was the integration of theory and practice. In typical scientific research, theorists calculate in one location while experiments occur elsewhere. In the Manhattan Project, these boundaries blurred. At Los Alamos, physicists developed designs and simulations, then engineers and metallurgists immediately applied them to prototype bombs. Problems could be solved iteratively if a theory predicted a neutron flux, technicians could build a small-scale experiment to verify it. This feedback loop accelerated progress at an unprecedented pace. The Manhattan Project's empire also nurtured innovation in measurement and instrumentation. The team needed to measure neutrons, radiation levels, and criticality with extreme precision. Detectors were invented and refined to capture fleeting events happening in microseconds. Oscillographs, ionization chambers, and radiochemical analysis became essential tools. Every measurement fed back into design calculations, ensuring that the theoretical models of chain reactions, energy yield, and critical mass were grounded in experimental reality. Importantly, the human dimension of the empire was as significant as the industrial and theoretical. The scientists, technicians, and laborers lived and worked under intense pressure. Deadlines were urgent, security was strict, and the stakes were immense. Yet, within Los Alamos, there was a culture of collaboration and problem solving that combined discipline with creativity. Social structures were built to sustain morale: communal dining halls, recreational facilities, and even informal musical and theatrical performances. Oppenheimer encouraged communication across disciplines, understanding that breakthroughs often came from unexpected conversations between theorists and engineers. The Manhattan Project also exemplified early big science, the notion that scientific problems of immense complexity require coordinated effort across multiple disciplines and institutions. From theoretical calculations to chemical engineering, from industrial production to mechanical design, every aspect of the empire was interdependent. This was no longer a laboratory experiment. It was a demonstration of how humanity could coordinate knowledge, resources, and manpower on an almost unimaginable scale. Even the smallest details mattered. Engineers at Oak Ridge had to maintain tolerances in machines that separated isotopes down to fractions of a millimeter. Chemists at Hanford worked in hot cells with remote manipulators to handle radioactive materials safely. Physicists at Los Alamos had to calculate implosion timings with microsecond precision. Each of these efforts required not just knowledge, but ingenuity, patience, and meticulous execution. By 1945, the Manhattan Project had become a fully operational scientific empire. Its laboratories had developed two types of bombs. Its plants had produced sufficient fissile material, and its personnel were ready for testing and deployment. Yet what made this empire extraordinary was not just its scale, but its synthesis of human intellect, industrial power, and scientific insight. It had transformed abstract theory into tangible reality, bridging the gap between the hidden energy of the nucleus and the capability to release it on a scale previously unimaginable. The Manhattan Project's empire stands as a testament to the potential of coordinated scientific effort. It was a massive, multi-dimensional enterprise where the boundaries between theory, engineering, and experimentation dissolved. It demonstrated that when knowledge, resources, and creativity converge, humanity can accomplish feats once thought impossible. And at the heart of this empire was a single, unifying goal: to understand and control the most powerful energy source in the universe, the atomic nucleus itself. By the time the Manhattan Project had taken shape, it had become clear that understanding fission and chain reactions was only part of the challenge. To build a functional bomb, scientists and engineers needed something more fundamental: fissile material. These are isotopes capable of sustaining a rapid chain reaction, atoms that, when struck by neutrons, can split, releasing immense energy. The two primary candidates were uranium 235 and plutonium 239, and the race to produce them would define the Manhattan Project's industrial and scientific strategy. Natural uranium contains primarily two isotopes: uranium 238, which is abundant but not easily fissionable, with slow neutrons, and uranium 235, which makes up less than 1% of naturally occurring uranium but is fissile. This scarcity presented a formidable problem. How do you separate a fraction of an element that is nearly identical to the rest of its isotopes in chemical and physical properties? The answer required innovation on an industrial scale, combining physics, chemistry, and engineering in ways never before attempted. The primary method, developed at Oak Ridge, Tennessee, was gaseous diffusion. Uranium hexafluoride gas, a chemically volatile compound, was forced through a series of porous barriers. Because uranium 235 atoms are slightly lighter than uranium 238, they diffuse just a little faster, allowing a very gradual separation. The process had to be repeated thousands of times in massive, carefully engineered plants. It consumed enormous amounts of electricity and required exacting control over pressure, temperature, and barrier composition. Each stage produced a tiny enrichment, but repeated enough, it yielded enough uranium 235 for a bomb. A second method, developed concurrently, was electromagnetic separation, inspired by the work of physicist Ernest Lawrence and his cyclotron at Berkeley. Uranium ions were accelerated through a magnetic field. Because uranium 235 is slightly lighter than uranium 238, it followed a slightly different path. By collecting the separated ions, operators could accumulate enriched uranium. This process, while effective, was slow, intricate, and labor-intensive, requiring massive electromagnetic calutrons, enormous machines that stretched over warehouses. Every piece of enriched uranium represented months of careful, exacting work. Meanwhile, a different approach was being explored for plutonium, an element that does not exist naturally in appreciable amounts. Plutonium 239 is created when uranium 238 captures a neutron in a nuclear reactor. Unlike uranium 235, which must be isolated from nature, plutonium can be produced in situ in reactors by irradiating uranium 238 fuel rods. This led to the construction of Hanford, Washington, home to multiple reactors designed for plutonium production. Each reactor was an immense, water-cooled structure containing tons of uranium fuel and moderated to control neutron speed. The chemical separation of plutonium after irradiation required highly specialized and dangerous techniques. Hot cells, remote manipulators, and shielded facilities allowed chemists to isolate the highly radioactive plutonium safely. Both uranium and plutonium production were feats of engineering. The Manhattan Project had to combine scientific precision with industrial scale. Thousands of workers operated massive plants, often without knowing the full purpose of their work. At Oak Ridge, entire communities were built to house employees, with strict security protocols to prevent information leaks. At Hanford, chemical engineers worked under constant exposure to radiation, relying on remote systems to handle dangerous materials. Every step required meticulous planning, trial, and error, a delicate balance between speed and safety. In parallel, theoretical physicists were performing calculations to determine the critical mass required for each isotope. Critical mass is not a fixed number. It depends on geometry, purity, density, and surrounding materials. For uranium-235, the mass required to sustain a rapid chain reaction in a bare sphere is roughly 52 kilograms. For plutonium-239, the mass is smaller, but the element is more reactive and presents additional challenges in bomb design. Understanding these details was essential. Too little material, and the chain reaction fizzles. Too much, and uncontrolled reactions could occur prematurely. The race for fissile material was also a race against time. Nazi Germany, it was feared, might be pursuing its own nuclear weapons program. Allied intelligence reported that German scientists were experimenting with uranium and heavy water reactors, and the Manhattan Project's leaders knew that producing sufficient fissile material first was crucial. Every delay, every technical obstacle could tip the balance in a global conflict. To accelerate production, the Manhattan Project embraced redundancy and experimentation. Oak Ridge contained multiple enrichment facilities using different methods: gaseous diffusion, electromagnetic separation, and thermal diffusion. Hanford built multiple reactors in parallel, ensuring that if one faced operational issues, others could continue production. This approach required vast resources, from electrical power to raw uranium, and relied on unprecedented coordination between scientists, engineers, and military planners. The technical challenges were immense. Uranium-235 and plutonium-239 are chemically identical to their more abundant counterparts, so chemical separation was largely ineffective. Neutron absorption in uranium-238 and impurities had to be minimized. The irradiation process for plutonium created large quantities of highly radioactive fission products, requiring careful handling and storage. Engineers designed remote-controlled machinery and hot cells to allow human operators to manipulate these dangerous materials safely, pioneering methods that would influence nuclear technology for decades. Security was a central concern. Entire facilities operated under military oversight. With strict compartmentalization, workers often handled uranium or plutonium without knowing the end goal. Communication was tightly controlled. This secrecy was not merely bureaucratic, it was essential to ensure that knowledge of fissile material production did not leak to enemy powers. The Manhattan Project became a model of need-to-know operational security, balancing rapid industrial-scale research with absolute confidentiality. Ultimately, the race for fissile material succeeded through a combination of theoretical insight, engineering innovation, and human perseverance. By mid-1945, sufficient uranium-235 and plutonium-239 had been produced to construct multiple atomic weapons. This achievement was more than the sum of its parts. It represented the culmination of years of coordinated experimentation, massive industrial effort, and scientific ingenuity. The Manhattan Project had transformed raw elements into tools of unprecedented energy, bridging the gap between theoretical physics and global-scale application. In this way, the race for fissile material was not simply a logistical or chemical challenge. It was the embodiment of human ambition applied to the deepest secrets of matter. Every gram of uranium 235 or plutonium 239 represented countless hours of labor, calculations, and problem solving. Every step brought the theoretical promise of fission closer to tangible reality, and every step carried the awareness that the energy harnessed in these tiny atoms could reshape not just science, but civilization itself. By the end of 1944, the Manhattan Project had mastered the production of fissile material. Uranium 235 and plutonium 239 were available in sufficient quantities for bomb assembly. The theoretical models of chain reactions had been validated. The industrial empire, built across Los Alamos, Oak Ridge, and Hanford, had delivered the raw materials needed to transform the hidden power of the nucleus into a weapon of unmatched energy. The stage was set for the final steps: bomb design, testing, and ultimately the deployment that would mark a new era in human history, when scientists and engineers moved from theoretical nuclear physics to working on actual weapon designs. They faced a core engineering problem: how to turn the latent energy of a nucleus into an extremely rapid, self-amplifying release of energy. Two fundamentally different approaches emerged because of the differing nuclear and material properties of the candidate fissile isotopes. One approach worked with uranium in a relatively straightforward manner. The other, using plutonium, demanded a far more sophisticated engineering solution. Understanding these designs requires looking at the interplay between nuclear physics, material science, and precision engineering, an interplay that drove many of the most inventive developments of the era. At the highest level, both designs share the same objective: assemble a configuration of fissile material that becomes supercritical so that each fission event, on average, produces more than one subsequent fission, and the reaction runs away exponentially. But how quickly and uniformly that supercritical configuration is achieved, and how it is held together for the brief instant required for a large yield, depends on the properties of the isotope and on engineering choices about timing, geometry, and surrounding materials. A useful way to think about the problem is in three interrelated domains: nuclear physics, materials and metallurgy, and timing, engineering control. Each domain places constraints on the others, and together they define the practical envelope of viable designs. Nuclear physics and isotope behavior. Different fissile isotopes respond differently to neutrons and have distinct spontaneous behaviors. Some isotopes have higher probabilities of undergoing fission when struck by a slow thermal neutron, others by a fast neutron. Some emit neutrons spontaneously at higher rates. Some create fission fragments that emit delayed neutrons, which can be crucial for control in reactors. These nuclear properties affect design choices in two major ways. First, the likelihood that an unintended neutron will start the chain reaction prematurely, so-called pre-initiation or pre-detonation, depends on spontaneous neutron emission rates. If an isotope emits neutrons at higher background rates, a slower assembly process increases the chance a stray neutron will trigger an early, inefficient reaction. Second, the neutron economy. How many neutrons are available per fission and how many are lost to non-fission processes constrains how much material and what configuration is required to achieve a prompt supercritical state efficiently. Historically, uranium-based designs leveraged isotope behavior that allowed a simpler mechanical assembly method to achieve supercriticality quickly enough. Plutonium's intrinsic nuclear characteristics, however, necessitated a different approach, assembling the core extremely rapidly and with much greater symmetry to avoid pre-initiation and inefficiency. Materials and metallurgy. The physical nature of the fissile material and of the materials placed around it matters profoundly. Metal alloys, phase behavior, density, and the mechanical response of materials under extreme pressures and temperatures are all important. Plutonium, for example, is a metal with complex and unusual metallurgical behavior. Its crystal structure can exist in multiple phases at different temperatures and pressures, and small changes in composition or temperature can produce significant volume changes. That makes plutonium metallurgy unusually challenging. It must be handled in forms that are mechanically stable and predictable for very precise engineering use. Plutonium's behavior under rapid compression also affects how effectively it can be turned into a dense, supercritical mass, uranium metal, while also demanding careful handling, has different mechanical characteristics, and was amenable to certain assembly concepts that did not require the extreme, symmetric compression that plutonium demanded. Surrounding materials, reflectors and tampers, are also selected for specific properties. A reflector can bounce escaping neutrons back into the core, increasing efficiency. A tamper adds inertia that slows the core's disassembly for a few critical microseconds, allowing more fissions to occur. The choice of reflector or tamper material involves trade-offs between neutron reflection, mechanical strength, and interaction with the fissile core, timing, shockwave symmetry, and initiation. Achieving the desired rapidity and uniformity of assembly is the central engineering challenge. Nuclear chain reactions proceed on timescales measured in microseconds to nanoseconds once a supercritical configuration is reached. Thus, the method of achieving that configuration must be not only fast but controlled in geometry and timing. One family of designs aimed to bring two or more subcritical pieces together very quickly so that they become a single supercritical mass. Another family compressed a single core inward, raising its density so that it becomes supercritical. Each approach has different engineering implications. Compression requires precisely shaped pressure waves that arrive with tight timing tolerances at many points simultaneously. Asymmetry results in inefficient compression and greatly reduced yield. Conversely, colliding subcritical masses must be brought together so fast that spontaneous neutron emissions cannot trigger premature fission during the assembly process. Initiation is another key topic conceptually. Once the core is in an optimal, supercritical state, a burst of neutrons is needed at the right instant to start the prompt chain reaction. Historically, scientists devised means to provide that burst in a highly time-controlled way. The timing of initiation relative to the peak supercritical condition affects efficiency, yield, and the course of the reaction. Engineers had to ensure that initiation occurred when the assembly reached maximum effectiveness. Mistiming reduces yield. or can cause a fissile. Design trade-offs and engineering solutions. Faced with these scientific constraints, designers pursued different engineering pathways. One approach favored mechanical simplicity, where the isotope's properties and the design allowed less rigorous symmetry and timing tolerance. The other required advanced techniques in explosive engineering, precision synchronization, and material science to produce a fast, symmetric compression. Both approached the same physical objective, but optimized around the material realities and the limits of available technology. A critical theme across designs was the need to minimize inefficiencies. Any neutrons lost to absorption by non-fissile components or escaping the core without causing fission reduce the fraction of the fissile material that actually undergoes fission while the core holds together. Hence, the reflector, tamper, the density achieved at peak compression, and the promptness of initiation all contribute to the weapon's efficiency. How much of the theoretical fissile material energy is actually released during the detonation pulse? Testing, diagnostics, and verification, because theory alone could not answer every question about complex, real material behavior during an extremely rapid energetic event. Testing and diagnostic measurements were essential. Instrumentation focused on measuring energy yield, temporal characteristics, radiation output, and the mechanical behavior of materials under extreme stress. Data from tests informed refinements in theoretical models and in the manufacturing tolerances required for reliable performance. These experimental programs were scientific endeavors in their own right, blending high-speed diagnostics, radiochemistry, and materials characterization from scientific principle to ethical boundary. It is important to close this section by restating a safety and ethical boundary. While scientific and engineering analysis can illuminate how different designs respond to physical constraints, providing operational instructions, construction techniques, or fabrication specifics crosses into prohibited territory. The historical record and publicly available scientific literature provide ample material for thoughtful, high-level study of the physics and the engineering challenges. Those resources also underpin modern work in reactors, medical isotopes, and materials science, peaceful applications that grew from the same scientific foundations. Wrap up, in short, the divergent paths taken for uranium and plutonium designs were driven by deeply rooted differences in nuclear and material properties. Those differences forced engineers to invent novel solutions in metallurgy, timing, and shockwave control, and to develop new measurement techniques to validate theories. The story of bomb design is therefore a story of physics translated into precise, demanding engineering, a demonstration of how fundamental properties of matter determine what engineering approaches are feasible, and how human ingenuity responds to the constraints of nature. Among the two fissile materials explored by the Manhattan Project, uranium-235 presented a unique combination of properties that made it amenable to a relatively straightforward, conceptually elegant approach, the gun-type design. While plutonium required an implosion method due to its nuclear and metallurgical characteristics, uranium's behavior under neutron bombardment and its lower spontaneous neutron emission rate allowed scientists to pursue a simpler, linear method of assembly. The design is historically fascinating, not only for its engineering choices, but also for how it illustrates the interplay between nuclear physics, material science, and practical problem solving during the Manhattan Project. The central idea behind the gun type approach is based on the principle of supercritical mass assembly. Uranium 235 exists in a natural state at a subcritical mass, too little material to sustain a rapid chain reaction. If one could somehow combine two subcritical masses quickly enough, the total system would exceed the critical mass threshold, and a self-sustaining, exponentially growing chain reaction would occur. This conceptual simplicity, however, belies the complex engineering considerations required to achieve it in practice. Nuclear considerations. The viability of the gun type method depends on several nuclear properties. Uranium 235 has a relatively low rate of spontaneous neutron emission, meaning that the risk of a stray neutron initiating a premature chain reaction is small compared to other isotopes. This property allows the material to be assembled over a finite, manageable timescale without catastrophic pre-detonation. The energy release from each fission event is enormous, but the critical mass must be achieved efficiently to ensure the chain reaction progresses rapidly before the assembly begins to disperse. Timing and geometry are crucial, even if less extreme than in other designs. Another important nuclear property is the neutron multiplication factor. For uranium 235, each fission event typically releases 2 to 3 neutrons, of which many can trigger further fissions. Engineers and physicists calculated the minimum mass, density, and geometric configuration required to ensure that once assembly is complete, the reaction proceeds to full yield before the core begins to expand. These calculations involved probabilistic models of neutron behavior, cross sections for fission, and considerations of neutron reflection and absorption by surrounding materials. Engineering and assembly concepts. In practice, the gun type approach involves bringing two subcritical masses together rapidly. The gun concept is an analogy rather than a literal firearm. One piece of uranium is projected toward another by a controlled linear mechanism to form a single supercritical mass. The key challenge is speed. While uranium 235 tolerates slower assembly than plutonium, it is still essential to bring the two masses together faster than any stray neutrons could cause pre-detonation. Precision in timing and alignment is critical because even minor deviations can affect the efficiency of the chain reaction. Another engineering consideration is the reflector or tamper surrounding the uranium with a layer of material that reflects neutrons back into the fissile core, increases the efficiency of the reaction, and reduces the total amount of fissile material required. The reflector must be carefully designed to maximize neutron return, while maintaining mechanical stability during the rapid assembly process. It is an example of how theoretical physics informs practical engineering choices, demonstrating the interplay between abstract calculations and physical construction constraints, material preparation, and metallurgical issues. Uranium 235 is chemically identical to uranium 238, so producing highly enriched uranium in sufficient quantities was an enormous challenge. Methods like gaseous diffusion, electromagnetic separation, and thermal diffusion were used to concentrate uranium 235. but each kilogram of usable material represented months of intensive effort across massive industrial facilities. The enriched metal also had to be fabricated into shapes that could be reliably handled and accelerated during the assembly process. Metallurgists had to consider factors such as density, purity, machining tolerances, and mechanical stability, ensuring that the uranium could withstand handling and the forces applied during the rapid assembly without cracking, warping, or introducing instabilities. Safety and control considerations. Even though uranium 235 has relatively low spontaneous neutron emission, the material is still radioactive and its handling requires care. Scientists and engineers designed methods for safe transport, manipulation, and assembly within highly controlled environments. The risk of accidental criticality was real, and redundant safety measures were integrated wherever possible. These considerations illustrate how engineering must account for both physical phenomena and human factors, balancing the need for precision with the realities of working with hazardous materials. Testing and validation. Before deployment, the gun type method underwent rigorous theoretical and experimental validation. While full-scale nuclear tests were not performed for the uranium design prior to operational use, small-scale experiments with subcritical assemblies and detailed simulations allowed scientists to verify neutron multiplication, timing, and assembly dynamics. Diagnostic tools measured neutron flux, density, and other critical parameters to refine theoretical models and reduce uncertainties. This approach reflects the Manhattan Project's broader methodology. Theory, computation, and laboratory validation combined to produce designs that were reliable and predictable under operational conditions, historical context, and deployment. The gun-type uranium design ultimately became the basis for the little boy bomb used in World War II. It represents a unique historical convergence of physics, engineering, and industrial production. Its development illustrates the Manhattan Project's strategic approach, leveraging the specific properties of uranium 235 to achieve a practical, effective, and conceptually simple design that could be manufactured and delivered within wartime constraints. While less sophisticated than the implosion method required for plutonium, it demonstrates how deep understanding of nuclear physics informs engineering decisions and drives technological innovation, legacy, and scientific insight. The gun-type design offers enduring lessons in applied physics. It shows how material properties, nuclear behavior, and engineering constraints interact to define feasible solutions. It also illustrates the importance of systematic research, iterative testing, and interdisciplinary collaboration, while the historical and ethical consequences of its use are well documented. The scientific achievement lies in translating complex theoretical insights into a tangible, functioning system, a feat that required unprecedented coordination across physics, chemistry, and industrial engineering. In summary, the gun-type uranium approach represents a carefully calibrated marriage of nuclear physics and engineering. Its elegance lies in using the isotope's favorable properties to minimize complexity while ensuring a rapid, reliable chain reaction. The design's development highlights the interplay of theoretical calculations, material science, mechanical design, and safety considerations, a vivid example of how scientific Understanding can be transformed into large-scale technological achievement, while the uranium 235 gun-type approach offered a relatively straightforward path to a nuclear explosion. Plutonium 239 presented an entirely different set of challenges that demanded innovation at the cutting edge of physics and engineering. Plutonium's unique nuclear and metallurgical properties rendered the gun-type approach impractical. Its higher spontaneous neutron emission rate meant that assembling a supercritical mass too slowly could result in pre-detonation, reducing yield dramatically. This necessitated a radically different engineering strategy, the implosion method, a design marvel that combined explosive engineering, precise timing, and advanced materials science. Nuclear properties of plutonium and design. Implications. Plutonium 239 is more reactive than uranium 235 in several critical ways. First, it has a higher rate of spontaneous fission, which releases neutrons randomly without any external trigger. In a weapon, this property increases the risk that a chain reaction could start prematurely if the fissile material is brought together too slowly. Unlike uranium 235, plutonium cannot simply be combined using a linear assembly. The assembly must be extremely rapid and highly symmetrical to ensure that the chain reaction occurs only when the core reaches full supercriticality. Plutonium's response to neutron flux and its physical density also influenced design choices. To achieve the desired yield, engineers needed to maximize neutron economy, ensuring that the majority of neutrons produced in fission would trigger further fissions rather than escaping the core. This requirement dictated careful attention to the shape of the plutonium core, the surrounding materials, and the timing of the initiating neutron burst. Any asymmetry or premature compression could reduce efficiency or produce a fizzle. Metallurgical complexities of plutonium. Plutonium is notoriously difficult to work with as a material. It exists in multiple crystal structures at different temperatures and pressures, known as allotropes, each with distinct densities and mechanical properties. Small variations in temperature or chemical impurities can cause significant volume changes, making the material unstable for machining or handling. Scientists had to develop specialized metallurgical techniques to produce a dense, homogeneous, and mechanically stable plutonium core capable of withstanding the intense compression of implosion without cracking or deforming. Additionally, plutonium is chemically reactive, forming oxides quickly when exposed to air and requiring careful handling to prevent contamination and corrosion. Its radioactivity presents further challenges, demanding that all fabrication occur in shielded, remotely controlled environments to protect workers while maintaining precise tolerances. The implosion principle, the central concept of the implosion design, is deceptively simple in principle. Compress a spherical plutonium core symmetrically using high explosives so that it becomes supercritical in a fraction of a microsecond. While conceptually straightforward, implementing this idea was extraordinarily complex. The compression must be nearly perfect. Any asymmetry results in uneven density, neutron leakage, and a failed or inefficient chain reaction. The implosion must be faster than the timescale of spontaneous neutron emissions to prevent pre-detonation. Achieving these conditions required groundbreaking advancements in explosive engineering, timing synchronization, and diagnostic instrumentation, explosive lensing, and shockwave control. A key innovation enabling implosion was the use of explosive lenses. These were precisely shaped charges designed to control the propagation of detonation waves, focusing them inward toward the plutonium core. By carefully arranging explosives of different velocities and densities, engineers could convert an outward propagating detonation into a converging spherical shock wave, compressing the core evenly from all directions. This technique required precise calculations of detonation timing, explosive geometry, and wave interactions, a field that was entirely new and required extensive experimentation. Achieving this perfect convergence was not trivial. Any deviation in the speed or shape of the shock wave could introduce asymmetries, reducing compression efficiency and preventing full supercriticality. To refine the technique, scientists at Los Alamos conducted numerous tests using inert materials and small-scale models, measuring the timing, wavefront propagation, and uniformity of compression with high-speed diagnostics. These experiments laid the foundation for the actual implosion design used in operational weapons, initiation, and neutron triggering. Once the plutonium core was compressed to a supercritical state, the chain reaction needed to be started in a controlled manner. Engineers developed specialized neutron initiators, small devices that emitted a burst of neutrons at precisely the right moment to begin the fission process in the compressed core. Timing was critical. The initiator had to fire when the core reached peak density, ensuring that the maximum number of fissions occurred before the core began to expand. This synchronization required microsecond level precision, integrating the physics of neutron emission with the mechanics of explosive compression, reflectors, tampers, and efficiency enhancement. The plutonium core was surrounded by a tamper, a dense shell that serves multiple functions. Mechanically, the tamper adds inertia, delaying the expansion of the core after compression and allowing more fission reactions to occur. Neutronically, the tamper can reflect neutrons back into the core, increasing efficiency. Material selection for the tamper required careful consideration. It had to withstand the forces of implosion, be dense enough for reflection, and not interfere chemically or physically with the plutonium core. In many ways, the tamper is as critical to the success of the implosion method as the core itself. Challenges in testing and scaling. Unlike the gun-type uranium design, which could be reasonably predicted with calculations and small-scale experiments, the plutonium implosion method required full-scale testing to validate theoretical models. The first test of the implosion concept was conducted during the Trinity test in July 1945. The successful detonation demonstrated that the combination of explosive lensing, precise core metallurgy, neutron initiation, and tamper design could reliably produce a supercritical reaction with a predictable energy yield. The test was a culmination of years of coordinated effort across physics, chemistry, engineering, and industrial production. A remarkable example of interdisciplinary collaboration at an unprecedented scale. Engineering as applied science. The implosion design exemplifies applied physics in its most demanding form. Every component, the plutonium core, the explosive lenses, the tamper, the initiator, was informed by theoretical calculations and validated through experimentation. Material science, high-speed diagnostics, shockwave physics, and nuclear theory were integrated to solve problems that had never been encountered before. The design illustrates how theoretical understanding of neutrons, fission, and nuclear chain reactions must be combined with practical engineering solutions to achieve desired outcomes. Legacy of the implosion method. The implosion method remains one of the most remarkable engineering achievements of the 20th century. Its development not only enabled the first operational plutonium bomb, but also pushed the boundaries of materials science, explosive engineering, and high-speed diagnostics. The principles developed during the Manhattan Project, precise wave shaping, high-speed measurement, and controlled compression, influenced a wide range of scientific and engineering fields beyond nuclear weapons, including shock physics, materials research, and high-pressure experimentation. On a cool July morning in 1945, at a remote site in the New Mexico desert, decades of theory, engineering, and industrial effort reached their decisive moment. The Trinity test was not merely a demonstration of a new weapon, it was the first time humanity had set off a device that converted a meaningful fraction of mass directly into energy. The event produced not only a blinding flash and a shockwave, but mountains of scientific data that would shape nuclear science for decades. In this section, we'll carefully examine what Trinity was, how the test was instrumented and measured, what the observed yield meant in physical terms, and how scientists analyzed the explosion to turn raw phenomena into rigorous scientific knowledge. Trinity's objective was specific: validate the implosion design, verify the predicted energy yield, and gather empirical data across a wide array of diagnostics. The test device, assembled and transported to the test site, was placed atop a steel tower to simulate an airburst, minimizing immediate ground coupling and allowing clearer measurements of light output, shock propagation, and fireball dynamics. Scientists and engineers worked for months to instrument the test site with an array of detectors placed at various distances and angles, each designed to capture a different facet of the explosion: optical brightness, pressure waves, radiation flux, seismic signatures, and high-speed photographs of the fireball's growth. Instrumentation for Trinity was remarkable for its breadth and ambition. Photographic and optical devices used fast shutters and rotating mirrors to record the evolving light pulse and the fireball's expansion on microsecond timescales. Pressure gauges and blast gauges, some buried, some at the surface, measured the arrival time and magnitude of the shock wave. Ionization chambers and Geiger counters charted the prompt radiation emitted at detonation and the subsequent residual radioactivity. Instruments recorded the electromagnetic pulse, air ionization profiles, and the timing of secondary phenomena, such as the formation of the characteristic mushroom cloud. Seismographs, at distances of many miles, registered the ground motion, turning the explosion into a measurable geophysical event. When the device detonated, the immediate sensory impressions were extreme: a flash brighter than the sun, a searing thermal pulse, and a roar of shock. Observers described a momentary, almost surreal silence after the flash, then the ground shaking as the blast wave arrived. The fireball rose rapidly, its core reaching temperatures of millions of degrees Kelvin in microseconds, ionizing surrounding air and creating a luminous plasma. From a physics perspective, the sequence of events was a textbook conversion of mass to energy. Through extremely rapid fission, the core's nuclei split in a cascading chain reaction, releasing kinetic energy, gamma rays, neutrons, and an intense thermal pulse. Quantifying the explosion's yield, the total energy released, was a principal focus. Yield is commonly expressed in equivalents of TNT, and the Trinity device produced a yield that, once analyzed, matched the range predicted by pre-test calculations. Scientists used multiple, independent methods to measure yield: blast overpressure readings and crater dimensions, high-speed optical radiometry of the fireball, seismic energy measurements, and post-test radiochemical analysis of residual isotopes and fission products. Cross-checking these independent diagnostics reduced uncertainties and provided a robust, composite estimate. Each measurement contained its own systematic and random errors. Triangulating among datasets produced the most reliable result. The fireball dynamics themselves were revealing. At detonation, the rapid release of energy created an initial spherical blast of extremely hot plasma. This fireball expanded and cooled, its luminous intensity changing as the radius increased and as radiation escaped. Optical measurements recorded the temporal profile of the light pulse, which ties directly to the energy release and the time evolution of the plasma. The shock wave, traveling supersonically, imparted pressure to the surrounding air and ground. Pressure gauges showed peak overpressures whose decay with distance matched theoretical blast scaling laws. These empirical scaling relationships, how peak pressure and impulse fall off with distance, became foundational models for predicting effects of other detonations at different yields. One unusual artifact of Trinity was the creation of a new geological material. The intense heat fused desert sand near ground zero into a glassy, greenish substance, now known as trinitite. The formation of trinitite was not only visually striking, it also provided material for radiochemical analysis. Samples contained fission products and activation products that served as fingerprints of the reaction. Isotopes, their distribution, and their chemical forms held clues about the nuclear processes and the interactions between the plasma and the environment. By chemically analyzing trinitite, scientists could infer how the fireball interacted with surface materials, how much material was volatilized and mixed into the plume, and the spectrum of isotopes produced. Radiation measurements provided critical information about both the prompt and residual components of the explosion. Instruments closest to the blast captured the prompt neutron and gamma flux that accompany fission. These prompt measurements validated theoretical predictions about neutron multiplicity and the energy spectrum of emitted radiation. Later surveys mapped fallout patterns, how radioactive particles condensed and fell back to the surface, revealing the roles of atmospheric transport, wind shear, and plume height in distributing contamination. Fallout measurements proved essential in understanding environmental impacts and in developing models to predict dispersion for future tests. Seismological data turned the explosion into a geophysical signature. The blast generated seismic waves that propagated through the earth and were recorded by instruments originally designed for earthquakes. Analysis of these signals allowed physicists to correlate seismic energy release with the bomb's yield. This relationship remains valuable. In later decades, seismology became a primary tool for monitoring nuclear tests worldwide. The Trinity test thus contributed to a body of knowledge that enabled indirect, remote estimation of explosive yields from seismic records, a technique with lasting implications for arms control and global monitoring. Diagnostic innovation at Trinity extended beyond hardware. Scientists developed mathematical models to connect raw instrument readings to physical quantities, blast scaling laws, fireball radiative transfer models, and neutron transport calculations were all refined using Trinity's empirical data. These models allowed the translation of transient measurements, pressure traces, light curves, isotope ratios, into statements about the physics of fission and the efficiency of energy conversion. One crucial diagnostic output was the efficiency, the fraction of the fissile material that actually underwent fission before the core disassembled. Efficiency was essential both for interpreting the yield and for guiding future design improvements. The Trinity test also offered lessons about the margins of uncertainty. Instruments could be damaged or saturated by the intense fields near the explosion. Sample contamination could complicate chemical analyses. Environmental factors like temperature inversions could alter fallout deposition. Scientists learned to design redundancy and diverse measurement types into their experimental campaigns, ensuring that no single instrument's failure would render the test's data unusable. This principle, diverse, corroborating diagnostics, became a hallmark of nuclear testing science. From a broader perspective, Trinity marked the first time empirical nuclear explosion data were systematically gathered and analyzed. The event transformed abstract predictions into validated physics and produced a rich dataset that informed weapon design, reactor safety, environmental science, and radiochemistry. Although its ultimate use was contentious, from a purely scientific viewpoint, Trinity established methods for measuring, modeling, and understanding rapid, high-energy fission events. Those methods, instrumentation design, multimodal diagnostics, and cross-disciplinary analysis, remain central in high-energy physics and shock physics research to this day. In short, Trinity was a scientific crucible. It converted theory into observation, produced new materials for analysis, and generated datasets that turned qualitative predictions into quantitative science. The test's yield analysis was an exercise in rigorous, multi-instrument verification, and its diagnostic legacy shaped a whole field, the empirical science of nuclear detonation measurement. When a nuclear device succeeds in producing a prompt, runaway chain reaction, the event that follows is not a single phenomenon, but a cascade of tightly coupled physical processes, nuclear, radiative, hydrodynamic, and chemical, all unfolding in microseconds and seconds. Understanding the science of the explosion means piecing together how subatomic events scale up to enormous macroscopic effects. A fireball that outshines the sun, a shockwave that scours the air, a flash of ionizing radiation that penetrates matter, and an evolving plume that carries heat and radioactivity into the atmosphere. In this section, we will examine those linked processes in a rigorous, non-operational way, tracing the sequence from prompt fission physics through fireball evolution, shock generation, radiation transport, and early environmental interactions. At the micro level, the explosion begins with the sudden onset of a prompt chain reaction when the fissile region reaches a supercritical configuration, neutron-induced fissions multiply exponentially. Each fission event releases kinetic energy of fission fragments, prompt neutrons, and high-energy gamma rays. The kinetic energy of the fragments is deposited almost immediately in the surrounding material, heating it on nanosecond to microsecond timescales. The local temperature rises to millions of degrees. Matter in the core and its immediate surroundings becomes an intensely hot, ionized plasma. This rapidly heated plasma forms the initial fireball. The fireball is not merely a luminous sphere, it is a dynamic, multi-layered structure in which radiation, electrons, ions, and neutral atoms interact. At very early times, the interior is optically thin to certain high-energy radiation, but opaque to lower-energy photons, giving the fireball a complex radiative transfer behavior. High-energy gamma rays and neutrons escape more readily at first, carrying significant energy outward, while lower-energy photons thermalize and contribute to the visible and infrared flash. The evolving spectrum of emitted radiation reflects this changing optical depth and energy partition. The thermal radiation emitted by the fireball produces an intense thermal pulse. This pulse contains visible and infrared light with a very brief, extremely bright peak, followed by a longer decay. The brightness and temporal profile of the thermal pulse depend on the total energy released, the altitude of the detonation, and the interaction of the fireball with nearby surfaces. Thermal radiation can ignite flammable materials at considerable distances, and the temporal structure, a very sharp peak followed by a tail, governs how heat is deposited on materials and surfaces. Simultaneously, enormous mechanical forces are generated. The sudden high internal pressure in the hot core launches a supersonic shock wave into the surrounding air. The initial blast front carries extreme overpressure and dynamic pressure. As it travels outward, the shock decays, but near the source it delivers crushing impulses capable of demolishing structures. The coupling between thermal energy and mechanical work is a central element of the explosion's destructive capacity. Some fraction of the nuclear energy is radiated, some is converted into kinetic energy of the air, and some is retained as internal energy of the heated matter. At the level of particle radiation, the event emits prompt neutrons and gamma rays with broad energy spectra. Prompt neutrons have a distribution of energies that influences subsequent interactions with the environment and with any nearby materials. Neutrons can induce activation in materials, transmuting stable isotopes into radioactive ones via nuclear reactions, and can penetrate shielding far more deeply than many forms of electromagnetic radiation. Prompt gamma radiation adds to the ionizing dose experienced by living tissue and sensitive electronics. The relative balance of prompt gamma and neutron flux, as well as their spectra, is determined by the fission processes and any subsequent neutron interactions with surrounding material. An often overlooked phenomenon is the electromagnetic pulse, EMP. The explosion produces a rapidly changing electromagnetic environment, ionization of the atmosphere, the acceleration of charged particles, and interactions between radiation and air create broadband electromagnetic transients. The intensity and frequency content of an EMP depend strongly on altitude and the electrical properties of the environment, but conceptually, It arises from the same sudden release of energy that generates light and shock, coupled to the behavior of charged particles in the plasma. As the fireball expands and cools, it entrains dust, soil, and structural materials. At ground or low altitude bursts, this process produces fallout, solid and liquid particles that condense from vaporized materials and acquire radioactivity through incorporation of fission products and activation products. The size distribution of particles, their chemical forms, and their aerodynamic properties determine how they settle, how far they travel, and how they deposit activity on the surface. Atmospheric conditions, wind shear, humidity, and vertical stability then govern the transport and deposition of these particles, turning an instantaneous event into an environmental process lasting days to years. The vertical dynamics of the heated column are governed by buoyancy and entrainment. The hot, low-density core of the fireball rises rapidly, creating an updraft that draws in ambient air. This action forms the familiar mushroom cloud morphology, a rising stem and a spreading cap. Within the ascending column, complex fluid instabilities mix hot gases with entrained particulates, leading to condensation rings and layers, whose structure reflects both the explosion's characteristics and atmospheric stratification. At high altitudes, the column can spread into thin layers that disperse radioactivity over great distances. At low altitudes, much of the material remains closer to the surface. Hydrodynamics plays a central role throughout these stages. Shockwave propagation through air follows scaling laws that relate peak overpressure and impulse to yield and distance. These empirical and theoretical laws allow scientists to predict, in a general sense, how blast effects diminish with increasing range and how structural loading scales. Near-field hydrodynamics, interactions between the shock and the ground, reflections from surfaces, and complex diffraction around obstacles produce localized amplification effects, including reflected shocks and Mach stems that can increase damage in particular regions. The interaction of the explosion with local materials produces a range of physical and chemical outcomes. Metals can be melted or vaporized. Soils can be sintered into glassy phases. Organic materials oxidize or pyrolyze. The high-temperature chemistry produces unusual species, ionized atoms, transient radicals, and condensed aerosols that later participate in environmental chemistry. Radiochemical transforms create a suite of isotopes, short-lived and longer-lived, each with its own decay modes and environmental behaviors. The isotopic fingerprint left behind provides scientists tools to study the event, reconstruct yields, and understand dispersion. Finally, diagnostics and measurement are intertwined with all these processes. High-speed photography captures fireball evolution, spectrometers analyze emitted radiation, pressure gauges and anemometers record blast data, and samplers characterize fallout composition. The synthesis of these diverse data sets translates transient, extreme phenomena into quantitative understanding. Energy partitioning, efficiency of fission, radiative transfer characteristics, and environmental dispersal models. In sum, a nuclear explosion is a tightly coupled multi-physics phenomenon. Nuclear reactions begin the chain. Radiation and kinetic processes drive the first microseconds. Hydrodynamics and thermodynamics sculpt the macroscopic fireball and shock, and atmospheric dynamics and chemistry carry the effects outward in space and time. Each facet is governed by well-established physics, yet their combination produces behaviors that require careful, multidisciplinary study to predict and understand. The scientific study of these processes has informed fields from high energy density physics to atmospheric science and remains a profound example of how microscopic events can cascade into planet scale consequences. A nuclear explosion releases energy in multiple forms, each with distinct physical characteristics, propagation mechanisms, and implications for the environment. Understanding how the energy is distributed between kinetic energy, thermal radiation, nuclear radiation, and residual radioactivity provides deep insight into the science of nuclear detonations without venturing into operational specifics. In this section, we will examine the physics of energy partitioning, the types of radiation produced, and the processes that govern the interactions between radiation and matter in the early moments of a nuclear event. Energy partitioning, the total energy released in a fission-based nuclear detonation, comes from the conversion of mass into energy according to Einstein's principle, ER-mc2 mc2 mc2. For modern fission devices, only a small fraction of the fissile material's mass undergoes fission, yet the resulting energy is enormous. Typically, the released energy is divided roughly into four categories: blast energy, kinetic energy transferred to the surrounding air and ground, producing the shockwave. This component can account for approximately 40–50% of the total energy in a typical fission detonation. The rapid compression and acceleration of air molecules propagates supersonically, generating high overpressure regions that expand outward in spherical or hemispherical patterns. Thermal radiation, emitted as intense visible and infrared light. This thermal component represents roughly 30–35% of total energy. The initial fireball radiates extremely high temperatures, producing an intense flash and heating nearby materials to extreme temperatures. Thermal radiation drives ignition, pyrolysis, and melting in exposed surfaces, and its intensity decreases with the square of the distance from the source. Prompt nuclear radiation, primarily neutrons and gamma rays, emitted within microseconds of the chain reaction, although a smaller fraction of the total energy, typically 5%. These particles interact with matter differently from thermal or mechanical energy. Neutrons, being highly penetrating, can induce secondary reactions in surrounding materials, while gamma rays contribute to ionization and radiative energy transport. Residual or delayed energy, including fallout, radioactive decay, and fission products. While this component initially carries only a few percent of the total energy, it becomes significant over hours to weeks, contributing to environmental radiation levels, deposition patterns, and long-term isotope transformations. Prompt radiation, neutrons and gamma rays. Neutrons produced during fission are high-energy particles that propagate at a significant fraction of the speed of light. Their interactions with nuclei in the surrounding material can cause elastic scattering, inelastic scattering, or secondary nuclear reactions. The spatial distribution and energy spectrum of neutrons are critical to understanding the energy deposition in both the device and its immediate surroundings. Gamma rays accompany neutrons in almost all fission events. Unlike neutrons, gamma rays are electromagnetic radiation, which interacts with matter primarily through the photoelectric effect, Compton scattering, and pair production. The combined effect is rapid ionization of air and matter in the vicinity of the explosion, contributing to heating, electron liberation, and secondary photon emission. Thermal radiation dynamics. The fireball emits thermal radiation as a combination of blackbody and plasma emission. Its intensity peaks within milliseconds of detonation and decreases as the fireball expands. Radiation propagates outward at the speed of light, and materials exposed to it experience rapid heating that can ignite combustibles, cause surface ablation, or produce optical phenomena such as mirages in the air. The temporal structure of the thermal pulse is essential. A brief, intense peak, followed by a longer decay, governs how heat energy is absorbed by surrounding materials. Shockwave energy. The kinetic energy imparted to the surrounding air manifests as a supersonic shockwave. The shock front is characterized by extremely high overpressure, followed by a rapid drop to ambient pressure. The initial impulse drives air and debris outward, creating blast damage that scales with the cube root of the energy released. Shockwave propagation is influenced by atmospheric conditions, ground topography, and the presence of obstacles, resulting in complex patterns of energy distribution. Radiation interaction with matter. The multiple forms of radiation interact differently with materials, producing effects ranging from heating and ionization to atomic displacements. Neutron flux can transmute stable isotopes into radioactive species, while gamma rays primarily deposit energy through ionization. Thermal photons transfer energy via heating surfaces, and shock waves mechanically accelerate particles. These interactions define how the explosion affects the environment, including atmospheric heating, ground scorching, and the creation of particulate matter. Secondary phenomena, fallout, and activated materials. As the fireball rises, it entrains dust, soil, and vaporized materials. Fission fragments and activated isotopes condense onto these particulates, forming fallout, which carries residual energy and radioactivity over extended distances. Fallout distribution depends on particle size, density, and meteorological factors. The radioactive decay of fission products contributes delayed energy release and prolonged environmental radiation. Electromagnetic pulse, EMP, a rapid burst of electromagnetic radiation accompanies the explosion, generated by ionized electrons in the air and high-energy gamma interactions. The EMP propagates at the speed of light and can induce electric currents in conductive materials over vast areas. While representing only a small fraction of total energy, it illustrates the diversity of energy manifestations and the coupling between nuclear events and the electromagnetic environment. Efficiency and yield. Not all fissile material undergoes fission before the assembly disassembles due to expansion. The efficiency, fraction of material actually fissioned, affects energy distribution. Higher efficiency results in greater proportions of thermal and blast energy relative to residual radiation. Analysis of yield and efficiency relies on combining measurements from blast effects, fireball evolution, radiation intensity, and radiochemical sampling Scientific significance. Studying energy distribution provides insights into the physics of extreme energy release, fluid dynamics, radiation transport, and nuclear interactions. The interplay between different energy forms demonstrates the interconnectedness of physical processes, and the empirical study of these effects has influenced fields ranging from high energy physics to astrophysics. In summary, a nuclear explosion is a multimodal release of energy distributed across kinetic, thermal, radiative, and delayed channels. Understanding how these components interact and propagate is key to interpreting observed phenomena, analyzing yields, and developing predictive models. The science of energy distribution illuminates the complex physics that govern one of the most extreme manifestations of matter and energy ever produced by human activity. The fireball produced by a nuclear detonation is one of the most visually striking and scientifically rich aspects of the explosion. Upon initiation of the chain reaction, the fissile core rapidly releases energy, heating the surrounding air and vaporized materials to millions of degrees. This creates an intensely luminous, expanding plasmasphere known as the fireball. Its growth follows well-studied physical principles. As energy propagates outward, pressure and temperature gradients drive a rapid expansion, and the fireball's interior remains ionized and optically thick during the first milliseconds. As the fireball rises, buoyancy plays a dominant role. Hot, low-density gases ascend rapidly, drawing surrounding air into the rising column, forming the characteristic mushroom cloud shape. The interaction with the atmosphere is complex. Entrained air cools the fireball, while turbulence mixes hot gases with entrained particulates. Layers of condensed vapor can form visible rings within the plume, and the surrounding wind field influences the cloud's tilt and ultimate dispersion. Atmospheric stratification, humidity, and temperature inversions also affect the fireball's expansion and the settling of fallout, demonstrating a tight coupling between nuclear physics and meteorology. Radiation transport within the fireball is another crucial aspect. High-energy gamma photons and neutrons escape, while lower-energy photons contribute to the thermal radiation seen externally. The optical thickness evolves as the fireball expands, determining the intensity and duration of visible light. These dynamics are measurable and provide critical information for understanding energy partitioning and validating theoretical models. Finally, the fireball's interaction with the ground produces local heating, melting, and vaporization of soil and structures. This generates new materials, such as glassy fused sand or trinitite, whose composition can be analyzed for fission product distribution. The atmospheric and ground interactions together transform a microsecond scale chain reaction into a visually and physically extended phenomenon observable over minutes, providing a natural laboratory for high energy density physics. The rapid expansion of the fireball launches a supersonic shockwave into the surrounding atmosphere. This shockwave carries the largest fraction of the explosion's kinetic energy and is responsible for much of the mechanical destruction at ground level. It initially propagates as a near-perfect sphere, compressing and accelerating air molecules to extreme velocities. Overpressure peaks can reach hundreds of atmospheres near ground zero and decay as the shock moves outward. Following scaling laws predictable from hydrodynamics. Shockwave behavior is influenced by environmental conditions such as temperature, humidity, and terrain. Ground reflections produce phenomena such as Mach stems, where overlapping waves increase local pressure and amplify damage. Measurement of these shock waves during tests provides valuable data for correlating energy release with observable effects, including structural damage, ground motion, and atmospheric response. The interaction between the shock wave and the rising fireball is dynamic. The hot, buoyant fireball modifies local air density, which in turn alters shockwave propagation. These feedbacks are central to understanding blast scaling and energy transfer. Engineers and physicists use these data to refine models for shockwave attenuation and to predict the spatial distribution of overpressure effects. Thermal radiation from a nuclear explosion is the primary source of visible and infrared light. The fireball acts as a radiating plasma, emitting energy in a near blackbody spectrum. The initial flash is extremely brief, but intense, reaching brightness greater than the sun, followed by a decaying tail as the fireball expands and cools. This thermal pulse can ignite flammable materials over large distances and causes heating effects that precede the mechanical shock. Its intensity and duration are determined by energy yield, fireball size, altitude of detonation, and atmospheric clarity. High-speed photography and optical radiometry during tests allow scientists to quantify the radiation flux, fireball expansion rates, and energy partitioning. Thermal radiation also drives local atmospheric effects. Heated air expands rapidly, producing micropressure waves, turbulence, and refractive effects visible as mirages or shimmer in the air surrounding the fireball. These observations provide real-time information about the coupling between radiative and hydrodynamic processes. Immediately following fission, the device emits prompt nuclear radiation, primarily neutrons and gamma rays. Neutrons, moving at significant fractions of light speed, interact with surrounding matter, inducing secondary nuclear reactions, ionization, and energy deposition. Gamma rays contribute additional ionization and carry energy outward from the fireball. The flux of these particles is extremely high in the first microseconds, but decays rapidly with distance and time. Their interactions with the atmosphere and the surface materials can be measured indirectly through activation products and radiochemical analysis. Understanding prompt radiation is crucial for modeling energy distribution, predicting initial environmental ionization, and validating physical models of the chain reaction's temporal evolution. Following the detonation, the rising fireball entrains dust, soil, vaporized material, and fission fragments. As the fireball ascends and cools, these materials condense into solid and liquid particles, creating fallout, radioactive debris that settles to the surface over hours to days. Fallout, particle size, composition, and density determine how far and how quickly it travels. Heavier particles fall near ground zero, while finer aerosols can remain suspended for extended periods and disperse over hundreds of kilometers. The chemical and isotopic composition of fallout reflects the fission process. Short-lived isotopes release radiation quickly, contributing to high-dose areas near the explosion, while longer-lived isotopes create prolonged environmental effects. fallout analysis provides scientists with essential data to back calculate yield, efficiency, and fission product distribution. Meteorological factors such as wind, temperature inversions, and humidity strongly influence the transport and deposition of fallout, demonstrating the complex interaction between nuclear physics and atmospheric science. Fallout also interacts with surfaces, soil, and water, initiating chemical and radiological transformations. Understanding these processes allows researchers to predict the spread of radioactivity, develop environmental models, and study the long-term behavior of radioactive materials in ecosystems. In essence, fallout represents the intersection of micro-scale nuclear reactions with large-scale environmental dynamics. When a nuclear explosion occurs at or near the surface, the intense energy release vaporizes soil, rock, and structures, forming a crater. The size and morphology of the crater depend on yield, depth of detonation, and ground composition. Near-surface detonations produce ejecta, solid and molten material propelled outward by the blast. The crater itself is a physical record of the energy partitioned into mechanical displacement and heating of surrounding material. Energy transfer to the ground contributes to seismic signals observable over tens of kilometers. Seismographs placed around test sites capture the amplitude, frequency, and timing of these signals, allowing scientists to estimate yield and energy efficiency. The interaction between the shock wave and ground also produces distinctive features in the ejecta blanket and soil glass formation, which can be analyzed for both structural effects and radiochemical content. Cratering demonstrates how nuclear energy is converted into mechanical work and material displacement, bridging microscopic fission events and large-scale geophysical effects. Nuclear detonations generate seismic waves due to ground coupling with the expanding shock wave. These waves propagate through the Earth as compressional P and shear S waves, measurable over vast distances. The amplitude and frequency content of the seismic signal correlate with yield, depth, and energy coupling efficiency. Seismic monitoring became a crucial tool for validating test yields and, later, for detecting underground nuclear tests worldwide. By analyzing waveforms, seismologists can distinguish between natural earthquakes and anthropogenic explosions. This involves assessing waveform shape, energy distribution, and arrival times of different wave types. The data also provide insights into energy partitioning between blast, thermal, and ground-coupled mechanical energy. Seismic analysis exemplifies how a microsecond-scale nuclear event translates into geophysical signals observable globally. Recording the rapid phenomena of a nuclear explosion requires advanced, high-speed diagnostics. Instruments must capture microsecond-scale events, such as neutron flux, gamma emission, fireball expansion, and shockwave propagation. Techniques include fast optical photography using rotating mirrors or streak cameras, radiometric measurements of thermal and gamma radiation, pressure gauges for shock monitoring, and ionization chambers for particle flux. Redundancy and cross-validation are essential. Multiple instruments measuring the same phenomenon ensure reliable data despite instrument saturation or damage. Analysis of these measurements allows scientists to reconstruct energy release fireball evolution, neutron distribution, and radiation transport. High-speed diagnostics also inform material behavior under extreme conditions, such as plasma formation, shock-induced melting, and vaporization. This combination of experimental rigor and theoretical modeling transforms a rapid, extreme event into quantitative, scientific understanding. One of the most important aspects of understanding nuclear explosions is energy scaling, how the energy released relates to observable effects such as blast radius, fireball size, and thermal radiation intensity. Physicists use empirical scaling laws, often derived from cube root scaling, which predicts that linear dimensions of blast effects increase proportionally to the cube root of the yield. For example, doubling the yield increases the blast radius by roughly 26%, while the thermal radius increases proportionally to the energy to the one-third power. Yield estimation is not trivial. Multiple methods are combined: blast overpressure readings, fireball radiometry, seismic data, and radiochemical analysis of fallout. Each provides an independent estimate of total energy release and efficiency. Cross-validation ensures accuracy, as single measurements may be distorted by local terrain, atmospheric conditions, or instrument limitations. Energy scaling is also vital for predicting effects in different environments. Atmospheric density, humidity, and wind influence shockwave propagation and fireball development. Models incorporate these variables to simulate the distribution of thermal, mechanical, and radiative energy, enabling scientists to predict outcomes under varying conditions. This methodology reflects how fundamental physics, empiricism, and computational modeling converge to understand energy release at extreme scales. The fission process produces a wide spectrum of radioactive isotopes, known as fission products. These isotopes are key to understanding both the yield and efficiency of the reaction. By collecting samples from fallout or test site debris, scientists can determine which isotopes were produced and in what quantities. The relative abundance of isotopes such as cesium-137, strontium-90, and iodine-131 provides insight into neutron flux, chain reaction dynamics, and the fraction of fissile material that underwent fission. Radiochemical analysis also helps reconstruct the temporal profile of radiation emission. Short-lived isotopes indicate prompt fission behavior, while longer-lived isotopes reveal decay pathways and environmental persistence. Techniques include gamma spectroscopy, mass spectrometry, and chemical separation methods. These analyses allow physicists to validate models of nuclear reactions, energy conversion, and environmental dispersal, bridging experimental observation with theoretical nuclear physics. Understanding how energy, heat, and radioactive particles move through the environment is crucial. Atmospheric dispersion modeling predicts how fallout travels, settles, and decays over time. Meteorological factors, wind speed, wind direction, turbulence, temperature inversions, and precipitation significantly affect the distribution of radioactive particles. Advanced models simulate vertical and horizontal transport, particle settling velocities, and cloud morphology. These models help estimate exposure levels, deposition rates, and long-range transport of radioactive material. By comparing modeled outcomes with observed data from historical tests, scientists refine predictive accuracy. Environmental modeling also incorporates radiative heating of the air, shockwave interaction with terrain, and plume rise dynamics, creating an integrated understanding of the explosion's environmental impact. The comprehensive study of nuclear explosions has yielded profound insights across multiple scientific disciplines. Observations from tests like Trinity enabled breakthroughs in high energy physics, hydrodynamics, radiation transport, materials science, and atmospheric science. Understanding how microscopic nuclear reactions translate into macroscopic blast effects has informed energy scaling, shockwave physics, and radiation modeling. Diagnostic innovations, such as high-speed photography, neutron detectors, and radiochemical sampling, advanced experimental techniques applicable far beyond nuclear weapons research, modeling the fireball, radiation, and environmental dispersion, fostered predictive methods now used in astrophysics, plasma physics, and environmental science. The legacy is not only technical, but also methodological. Nuclear testing demonstrated the integration of theory, experiment, and large-scale engineering in a coordinated scientific enterprise. While the historical and ethical contexts are widely discussed elsewhere from a purely scientific perspective, these efforts illustrate how extreme physical phenomena can be measured, understood, and modeled with remarkable precision. Now, with a smile on your face, you'll have a good understanding of the atomic bombings, not just as moments in history, but as scientific triumphs that forever changed how we see energy, matter, and ourselves. Good night, dear friend. Sleep well, and see you next time.